In the last lesson, we learnt that sound is a longitudinal wave. That means that the wave vibrates in the same direction as the direction of travel. So, as the sound wave is travelling from the speaker to the air, the particles of air in the medium are vibrating backwards and forwards in this direction, parallel to the direction of travel. We also learnt that these vibrations sets up regions of high and low pressure as the wave travels. Where the pressure is at a maximum, we call that the region of compression, and where the air pressure is at a minimum, we call that the regions of rarefaction. Now, in order to analyse the sound wave, what we've done here is we've taken a snapshot of the pressure changes as the wave travels. Now, if we were to represent these variations in pressure on a graph, they would look like this. Okay, so we can write pressure here. So we can see that there is a sinusoidal variation in pressure with distance. Now, the distance between two high pressure peaks, that's to say between two regions of compression, say from here to here, is what we call the wavelength of the sound. And the wavelength is given the symbol lambda. That's a Greek letter. Now, this snapshot shows us how the wave changes in space as it moves from one place to another. But we're also interested in seeing how the wave changes with time at a fixed position. So, what we're going to do that is we're going to do an experiment, and we're going to replace our ear with a microphone. Okay, and the microphone is attached to a device called an oscilloscope. An oscilloscope helps us to see how the wave changes in time. So what we're doing now is we're examining right at this point here how the wave changes with time. Whereas before we were looking at a fixed point in time at how the wave changed in space. Now we're looking at a fixed point in space at how the wave changes with time. And we use the oscilloscope to do that. Now, just have a look at this oscilloscope screen. Now, we're going to imagine that this speaker here is vibrating at around about middle C. We're going to call that, just to keep life simple, we're going to call that 250 Hertz. That's to say it's completing 250 cycles every second. In fact, what that means is that every single air particle between the speaker to the microphone, and including the microphone membrane, is also vibrating at that same speed of 250 cycles per second. So the frequency right across space is constant. And the oscilloscope picks up these vibrations. Now, the oscilloscope screen, again, as I said, helps us to measure very small periods of time. All right, and each of these little grids here represents, in this particular case, 0.001 of a second. That's to say, that's equal to 1 millisecond. So you can imagine, a particle here. Right, what we're doing here on the oscilloscope screen, we're measuring how it vibrates, going that way, down to the middle, back again, then back again with time. Okay, and that's recorded in a vertical sense here on the screen. All right, so the particle moves up, goes back to the middle, down again, back to the middle. All right, and we record how long it takes to do that. So looking at the screen, we can see that to complete one cycle, that's to say, to go from here to the peak, back again to the trough, then back again, is equal to exactly 1, 2, 3, 4 squares. So we can say that's 0.04 milliseconds. Now, the distance here between the two peaks or the two troughs, is called the period. Okay, call that the period. And the period is given the symbol big T. Again, in this particular case, T equals 0.004 seconds. Now, you remember in the last lesson we mentioned that the frequency of a wave, that's to say how quickly it's vibrating, is equal to the number of cycles that it completes every second. So if it's got a high frequency, then it's vibrating around completing a high number of cycles in a second, and if it's got a low frequency, then it's a low number of cycles per second, and that affects the pitch. So a high frequency sound has a high pitch, and a low frequency sound has a low pitch. That's to say, the particles are vibrating backwards and forwards slowly. Now, again, as I said, this oscilloscope is measuring how quickly they vibrate, and there's a relationship between the period, that's to say the time taken to complete one cycle, and the frequency of the wave. And we say that they are inversely proportional to each other. So the frequency of a wave is equal to 1 over the period of the wave. Now you'll notice that in this particular case the period is 0.04 seconds. So we can calculate, knowing the period so we can calculate by measuring the period on the oscilloscope, we can calculate the frequency that's being produced by this speaker. And it is, as I said earlier, F is equal to 1 divided by, in this case, 0.004 seconds, 0.004 seconds, which is equal to 250 cycles per second, or hertz.